Hello and welcome back. Today's discussion will be delving further into minerals and focus on silicates, the formation of minerals and mineral properties. As mentioned previously, silicate minerals make up a majority of the rocks in the Earth's crust, such as quartz, feldspar, and olivine, and other clay minerals. We have talked previously about lattice structures and how they form nice three-dimensional crystals. When dealing with silicate minerals, they form a silicate tetrahedron shape with silicon in the middle surrounded by 4 oxygen atoms. These tetrahedron shapes can combine in a variety of different configurations, such as in the case of olivine group of minerals, and is popularly known as the green gemstone peridot. As I mentioned, the tetrahedron shape can combine to form pairs, rings, single chains, double chains, sheets, and/or frameworks by the sharing of the oxygen atoms. Quartz is a well-known silicate mineral and is a framework of silica tetrahedra and has a simple silicate composition because it only contains silicon and oxygen. However, the most abundant group of minerals in the Earth's crust is known as feldspar and are composed of silicon, oxygen, aluminum, and either sodium, known as albite, potassium, known as K-feldspar, and calcium, known as anorthite, or some combination of all 3 of these. Another common group of silicate minerals rich in iron and magnesium are mafic rock and can also be referred to as ferromagnesian and are dark-colored, typically black, brown, or green. We talked about olivine, and I just want to point out that this is a ferromagnesian mineral. This brings into question, how do minerals form? Well, this can be through a number of different processes, for example, through evaporation. When the dissolved minerals are left behind, minerals form. In addition, metamorphism, which is the alteration of a rock or change of a mineral that has undergone heat or pressure. In addition, majority of the minerals in rocks around us are a result of the cooling of magma, which is molten or partial molten rock. As magma begins to rise, it can cool, and depending on how quickly it cools, depends on the formation of the mineral and the size of the crystal that forms. The faster the cooling process, the smaller the crystal, versus if it takes prolonged amount of time to cool, such as over years, the crystals are larger in size. For example, the group of silica minerals known as micas forms when magma has rapidly cooled. Micas are silicate minerals known as sheet silicates, and there are about 37 different mica minerals. It is important to note that stacked silica sheets do not have strong bonds, so they can be broken apart relatively easily. As we begin to delve deeper into minerals, it is important to mention some common mineral properties that are used for identification purposes. We have color, streak, luster, hardness, crystalline structure, cleavage and fracture, and density. Let's start talking about color. It is important to note that color is not a reliable source to determine what mineral you have, but is used to describe the property of a rock. When we refer to the color of a sample, this is in reference to the physical surface, which can be variable depending on the type of surface. In order to get a better indication of the sample's actual color, a streak test is performed by scraping the corner of the sample on an unglazed piece of porcelain. The result of this test gives a better indication of the true color. For example, take the following 2 rocks and look at their streaks. Both streaks leave a reddish-brown color on the porcelain tile, and the rock on the left is a metallic hematite, and on the right is an earthy hematite. Regardless of it being metallic or earthy, hematite always leaves a reddish-brown streak. The next characteristic is luster, which is the way light reflects the surface of a mineral. For example, metallic samples' light does not pass through them, giving them that metallic look, whereas a non-metallic mineral, light is able to pass through them. For example, if you have a reflective surface, then you would refer to it as glassy. Whereas a dull, non-reflective sample has an earthy luster. Some other common luster names are silky, pearly, and resinous. Another important diagnostic property of minerals is hardness, which we use the Mohs scale from 1 to 10. Hardness is the ability of a mineral to resist being scratched by another mineral. In order to determine this, you literally scratch the minerals together to determine where on the scale it lies. Hardness does not identify a mineral. The hardest natural mineral on Earth is diamond. Crystalline structure along with chemical composition can be used to distinguish it from other minerals, and we have discussed this in depth already. The next physical property is cleavage and fracture, which describes how a mineral breaks Cleavage occurs when a break is along a flat planar surface, whereas a fracture is not as clean and is an irregular break. The way a sample breaks is dependent on its atomic arrangement and how weak or strong the lattice structures are. The last physical property we'll discuss is density, which is the measure of a mineral's mass over unit volume. As a brief overview of the discussion, we went over silicate minerals, formation of minerals, and mineral properties. Thank you and have a wonderful day.
1, 2, 3. Geology.